I always get very excited when we start talking about computational limits here. So previous to this, we talked about linear search. We talked about a proof of correctness for linear search, and we established that that algorithm runs in big theta of n time, or big O if you prefer to talk about it in those terms. It runs in linear time. Now, it would be nice to know whether that algorithm is going to be among the class of algorithms that are the best known ones to solve the search problem. Now, remember, in our problem, we're just given a set of elements. So in our case, we thought of it as just an array. We have no previous knowledge about what's going on inside of here, right? I must stress that the arguments I'm going to be making here are rather general for some things, but the big point is that we sequentially check each one of these to determine if a value that we're given is in one of the spots. We want to know if it is there or isn't there. So to do this, we're going to be establishing an idea of a lower bound. So just to give you kind of a big view of this, so we're going to talk about lower bounds. So consider this more of a high-level explanation. If you find yourself curious about us doing more of a delicate exposition into this topic, please just let me know. I'm always happy to go exploring this. So very often when we talk about a problem, so suppose I give you a problem that I would like to solve. So a computational problem specifically. So I give you some problem. Each of this consists of different problem instances. We feed these to an algorithm. And we say that the algorithm is correct if for every one of these instances it produces the solution, or thus the optimum, or whatever it might be for the given type of problem. So what we like to do is we'd like to know what's the most efficient way to solve the problem. Now, that's a very broad question, and it's very hard to establish if we actually have the best known algorithm. It's a very interesting and fundamental question. Especially that we're given our search problem is where we're given a collection like this where I don't know what's inside of here at all. So I must stress that we have kind of two concepts. We have the idea of an algorithmic upper bound. So an upper bound. So this would be the time complexity, or whatever complexity you're curious about. So in our case, usually think of it as time complexity, the worst case time complexity. So the time complexity best known to solve the problem. So this is some algorithm that we have. So for example, if I were going to consider like our search problem, this might be perhaps, this is linear search. In fact, it is in this case. So linear search in our example with the search problem would be, provides us an upper bound on how efficiently we can solve this problem. So likewise, there's this concept of a lower bound. So this is the required time to solve the problem. We'll say required time complexity to solve the problem. There's a lot of these discussions when it comes to different types of problems. So sorting is one where this very often comes up when you learn about some of this stuff. Searching is another one, so I'm going to focus on that. So you know when the problem is essentially solved, or at least you can start narrowing it down even further, once the upper bound and the lower bound are the exact same, or at least very close to each other, and there may be a pretty good reason why they can't be. Or at least we lack the methods to do so. The point is that it's a very interesting research question. If you can get these two to be equal to each other, you could basically close the book and say the problem solved, right? You can't make it go any faster. However, after that stage, there may be further refinements you might make. For example, the problem of sorting has been, in this sense, solved for decades. But people still keep talking about sorting algorithms because it's a very fundamental question, or a fundamental problem that computer scientists and generally people that like to sort data might want to have. So there's a lot of different sorting algorithms out there that even then, some people came up with these kind of results. Well, the thing is you could always narrow what exactly you want the sorting algorithm to do, just like you could do the same thing with the search problem. So in our case, we're going to be considering when we have an array, we don't know there is nothing we know about what's going on in here. All we know is that they are going to be equal to the value, or they're not going to be equal to the value. So That being said, let's talk about this. So you might ask, Dan, how the heck do you prove this? Like we know we could present an algorithm, analyze its running time, and if it's the best known one we currently have, then it falls under the UB category, the upper bound. So it's like an algorithmic upper bound on how efficiently we could solve it. Likewise, lower bound, well, what can you do? One thing that you're going to notice very quickly is we cannot make assumptions about too many things, right? Those assumptions will limit our results. So the big thing is that we cannot assume one specific algorithm, right? We can't. That doesn't tell us the time required to solve the problem. We can introduce other constraints, for example, that might be interesting. For example, say one that will come up in a little bit is like, oh, well, suppose that the array is sorted. And suppose that the elements have a special property where you can compare them, say one's less than the other or they're equal. These are specialized assumptions that we can make to help us better understand how we can solve the problem. But notice that I'm not making any assumptions about what the algorithm is. I cannot make assumptions about the algorithm. I can make assumptions about perhaps what the algorithm is capable of doing, for example, but not specifically what the algorithm, like one specific algorithm, because that doesn't ultimately tell me a lower bound on how efficiently we could solve the problem. But here's the thing, when you break it down to a class of algorithms, like based on what computations it's allowed to do, then you got yourself something, at least a good starting point, so that you can ask natural research questions from there that either could generalize those research questions or they might be more narrow, which is a very natural place for a lot of this discussion to go. So this brings me to talking about what we're going to talk about here. We want to establish a lower bound for the search problem as we defined it previously. So one way to do this is by using what we call an adversarial argument. So you might ask, Dan, what do you mean by an adversarial argument? So I must stress that the way I'm going to introduce you to this is going to be somewhat informal, but I'm hoping that by the end of this you'll get kind of the gist of the idea. Like I said, if you're curious more about this, I'm happy to talk more about it in a future video. So I must stress before I get into this. Sorry, I'm really bumping this up. You got to think of this adversary as something imaginary. It's something to help us craft a discussion around what if we give you any one algorithm, can you give me an instance that will always cause a given algorithm to perform as many operations as necessary to establish a lower bound? So it has to do at least this many things for any one algorithm under our presumptions. In our case, we're just checking if they're equal or not equal, which I think is a rather it's a very, very basic kind of assumption that you can make for our problem, because we need to know if it's in there or not. It's kind of integral to the problem itself. So I must stress that this adversary, there's a lot of ways you could think about the adversary. There can be different kinds of adversaries, like based on what they do and what they are capable of doing. So I must stress, however, this is an imaginary concept, just to make it easier for us to think about how we can construct instances that always will cause the algorithm to perform at least some number of operations. Hopefully that is clear. So you got to imagine it like I give you an algorithm. So suppose we have an algorithm that asks questions. So you can think of these as guesses about the input. And remember, we are not assuming any one algorithm. This is going to be where we just presume it's some algorithm. It makes guesses about the input. So in our case, this would be very simple. Is X in the array? So naturally, one way you can do this is you can ask, is X in this box? Is X in? this box, sorry, I'm just dying by the excitement of this. Is X in this in this box? X is in this box. These are guesses. That's what I mean. It's a bunch of questions we're asking. Now, this is where the adversary comes in. So suppose that this adversary can craft for each question a worst possible answer to the question. A worst possible answer to the question. But here's the catch, though. The adversary can't just make up anything. The answers have to make it so that it's at least going to give you one input, or i.e. problem instance of your given problem. So it's going to craft an instance. It's going to make one out of these guesses. But so it has to be consistent with one problem instance at least. So you can't just make it so it makes up something that the algorithm would never be attempting to solve, right? It has to be consistent with one input. So the answers must be consistent. Sorry, my writing is just melting today. Must be consistent with one problem instance. So here's the catch. Imagine you're playing a game with somebody. Suppose you're playing, I'm not sure if you've ever heard of the game called Battleship, for example, or another game called Mastermind. In these games, the way it works is that you have somebody you're playing with. It's like a two-player game. Suppose you give me the idea of Mastermind. So Mastermind is a game that works like this. Now, it may have different names. It has some pegs. And they're hiding behind some guard. And the other player, this would be you playing, you have to guess the color pattern of these pegs that go into these holes. So you put colored pegs in, and if it matches the pattern, what happens is that information will get revealed to you. But the thing is, you get a certain number of guesses, and this player wins if you don't guess the pattern. So say, for example, this one's a black, this is white, this is black, that's white. Suppose that I put a black one here and say a white one here, but I put two blacks. That's not a correct guess. The player I'm playing against will tell me how many I got correct, but they won't tell me which ones. Well, you can imagine this like in our concept here. Suppose that this adversary has the ability to know the order of your guesses because they'll know about your algorithm. So what they could do is they could craft an instance for your one given algorithm, which, remember, like I said, you can't presume any one specific algorithm. You have basic assumptions based on the type of algorithm. By adding more assumptions, you restrict the possibility of your result generalizing. So suppose you have these guesses. Every single time, suppose that this adversary, every time you made a guess, you can almost imagine it like the adversary has the ability to know what you're going to guess next, so that the adversary can switch around these pegs without you knowing that you're about to make a guess. But the adversary will know how to switch these pegs around so that you keep guessing until you get the very last guess. And then it will say, hey, look, you got it. But the thing is, the adversary is essentially cheating, but cheating enough that they're cunning enough that they'll give you something that's consistent with an instance that the algorithm would have to solve. So this is a little abstract at first, but here's the idea. The adversary is going to build an instance, and then you look at what this instance does, and regardless of what the algorithm is. But the whole idea is that this adversary is going to be malicious. It's going to try to cause the algorithm to perform as many guesses as possible in the worst case. So it's going to try to get it so you have to perform at least a certain number of guesses in order to solve the problem instance that gets crafted, regardless of what the algorithm is. So hopefully you get the idea. So I'll show you an example of what I mean by this. So I'll give you the formal idea behind this. So here's the formal idea. We will show for every algorithm A and input size n, there is some input. So this will be selected by the adversary. That's the kind of the imaginative part about the adversary. Input of the problem of size n, where A takes at least L of n operations, where L of n is the lower bound. So whatever we try to make L of n as, or this function L, we want to make it so that it is as large as possible. So we want to make this lower bound as large as possible so that we can get an idea of how efficiently we need, like how much we have to do at least. So if we can make that at least as big as possible, then it gives us an idea of how much work we need to do and see if we could come up with an algorithm to match that. If we have a very poor lower bound, it may not mean anything significant for us because we just lack a good technique to prove it. So this is a theoretical concept. Just be clear. We're not talking about one given algorithm. We're talking about any one algorithm requires this. So under the presumptions I've made. So in our case, we're going to presume that we know it's either equal or not equal. So that's a pretty broad generalization. So one algorithm I gave you already is linear search. So I just wanted to remind you what linear search does. So remember, linear search is just one algorithm. There can be other algorithms too. So something I wanted to talk to you about to just kind of make this adversary concept a little bit more clear, I'm going to use our boxes over here to help explain this idea to you. So you got to imagine this. When you give me one algorithm, often I want to know how long it's going to take to solve the problem for any one instance of a given size. So for example, linear search takes big O of n time, right? So what did we do to establish that? Now, in our way I wrote linear search, it made it easier for us to prove the claim, but you could have easily showed that if I wanted to make it so it exit out of that loop much faster, I could just simply have a return statement inside of there and just say return true when I find it, right? Well, in the worst case, it would just simply be that X isn't in the array, right? Well, in linear search, what we do is we scan from left to right, go position by position, and we check inside of each one of these, and we see if it matches X, right? See, here's 6. If X was 6, then I would have found it, and my found would be set to true. I would know that it's in there, and that'd be all I need to do. Well, in the worst case scenario here, I want to have it so X isn't in here so that I go through all of these boxes, right? Well, I don't know what order my algorithm might actually do them in. So for example, I could give you another algorithm, for example, just like linear search, that goes through all the elements from right to left instead of left to right. Suppose instead what it does, perhaps it may even go this position, maybe go into this one next. Sorry, that was a little loud there. So it goes into this position, then it goes to this position, and then it starts going through all the odd positions. Well, actually, these would be technically this would be even, odd, odd. Yeah. See, the numbers are right on the boxes. So we need to keep in mind that all I have capable of checking is x is an L, as in x is equal to L sub I for some position, or we don't. So I don't know what order the algorithm would even examine these. It may even not even examine them at like all just one by one, right? So I need to keep that in mind. So what I'm going to do is my adversary is going to come up with a way. So suppose, for example, suppose that I was given an instance where I given the array L, a value x, and n for the length of the array. So for example, suppose that I always give it a value that is not in the array, always. Well, regardless of what order you actually examine these in, it will never equal the value x. So what I need to do is every single time I'm going to construct the instance. So when I build the instance, I'm always going to make it so that it never will eventually find this value x. Or, even better, if I want to make this even more playful for the adversary, what I could always do is just make it so that it just simply finds x in the very last spot every single time. But the thing is, once I know what the algorithm, what order the algorithm checks, whether they're equal or not equal, then I could just simply craft an instance that will have this behavior, regardless which algorithm it is. So that's where the adversarial argument really goes from here. So let me sketch out this with an adversarial argument. Anyways, where I was, so reminder, remember the goal here is for our adversarial argument is to craft an instance, regardless what the algorithm is, that will require it to perform at least some number of operations. So here's a theorem. So given an array L of n elements, the search problem cannot be solved in little o of n time. So I mean worst case time. Another thing you might ask is what the heck is a little o? So the little o is, so you know how in big O we have an asymptotic upper bound. Now this is an asymptotic upper bound too, but it is a strict upper bound. So that means that this is saying, so this will consist of all the complexity functions that are not linear ones, but it may consist of the like logarithmic functions, constant functions, but it will not contain the linear ones. It has to be all of them of order less than n. So another way you can rephrase this is saying is it requires what we call big omega n operations. So here's how the proof's going to go. So here's how the adversarial argument will go. So suppose algorithm A, so I don't know what algorithm A exactly does, it just solves the search problem. That's all I know. That's all I know, guys. So the order A examines elements. Now I must stress that these are just the order we examine the elements. It may not be exact, like they may consider multiple elements over and over again, but these are the order the elements are first considered, okay? It examines elements is as follows. I0, I1. So these are a whole bunch of indices or positions for an array. Like I said, these could be potentially visited more than once by your algorithm. The point is that this is the order that they get examined in by first appearance. So construct, and this is what the adversary will do, is construct array L so that L sub I0, L sub I1 all the way up to L sub I n minus 2 are all not x. But L sub I n minus 1 is equal to x. So if this happens, right, this is the order that they're considered in. So if all of those are not x, that means that you have not found x in L. However, by the time you get to the last one you've first revealed, that is x. So keep in mind, this is one such way you could build an instance regardless of what the algorithm is. So A examines, because how many indices are there? N of them, right? So A examines n elements regardless. So the point is that it's at least n. It has to examine n of them. Regardless. Therefore, at least big omega of n comparisons are required. And that's the end of the proof. End of the proof. So, talking back to our discussion about upper bounds and lower bounds, notice that this claim is saying that you cannot solve the problem any better than linear time. That's what this is saying in plain language. So it means that if you give me linear search, and linear search runs in linear time, asymptotically speaking, it's optimal with respect to time, right? Because that runs in big O of n or big theta of n, and this claim is actually saying that no, you can't do any better than that. So we could say linear search is the best known, well, it is among the best known algorithms to solve the search problem, right? So piece of cake, right?